Hello, everyone. We're going to start Chapter 2, Atoms, Molecules, and Ions. We have previously finished Chapter 1. Hopefully you've gone through those slides. Chapter 2 now, so only about 9 more to go. So in the early 1800s, a little about chemistry, John Dalton, son of Mr. and Mrs. Dalton, he came up with three postulates. One, every element is composed of extremely small particles called atoms. This is what we know now. However, this is quite a discovery in the 1800s. All atoms of a given element are identical to one another in mass and in other properties. So if you have H2O, two H2O molecules, they have the identical properties. We have the law of conservation of mass, meaning if I have a reaction in a sealed container, if we add two elements, measure their mass, the product will have the same mass as well. None of the mass can escape from that particular container. And number 4, law of constant composition. H2O is always going to be 2 hydrogens for every 1 oxygen. Okay, so for the next few slides, there's no math involved, no calculations. For my class, I would ask to do, so just to follow the theory. The law of conservation of mass will focus on number 3. As I said, if I had 1 gram of H2 and 8 grams of O2, I did a reaction, added heat and did a chemical reaction to give us H2O, we would get 9 grams of H2O. So law of conservation of mass, whatever is on the left side should equal on the right side if it's in a sealed container. Law of constant composition, as I said, for a water molecule, it's always 2 hydrogens atoms for every 1 oxygen atom. CO2 is always 2 oxygen atoms for every 1 carbon atom. To continue with law of multiple proportions, here we see, if we look at CO2, which if I were to measure 8 grams of oxygen for every 3 grams of carbon, if we were to compare that with carbon monoxide, and we were to measure the masses of the particular elements, we'd have 4 grams of oxygen and 3 grams of carbon. And the ratio between CO2, the oxygens, in this case, the oxygens, the ratio here is 2 to 1. And you'll see that in the mass of the oxygens here, in a blue square, 8 grams for every 4 grams. Okay, so the law of multiple proportions states that the ratios will be consistent throughout. Again, if this is an experiment where they actually measured the mass of each particular element, if the compounds here on the left, where they vary the amount of oxygens, except for the first case, here if the mass of nitrogen is consistent, 1 gram all the way down. If we were to measure the mass of oxygen, they would vary and its course to its corresponding compound. So let's just look at the second one here. NO, nitrogen monoxide. We have here 1 gram of nitrogen and 1.14 grams of oxygen. This was experimentally measured. If we were to compare that with NO2, and we had the 1 gram staying the same for nitrogen, the difference between NO and NO2, the mass of the oxygen would be 2 times greater. So it's 2 times greater. 2.28 is 2 times greater than 1.14 grams. And we take it another level. If we compare NO to NO4, the difference between the oxygens is 4 times. This, of course, we would have the mass of nitrogen would have to be consistent at 1 gram. And in the case when we go from NO to N2O, the mass of nitrogen still 1 gram, and if we look here between 1.14 and 0.57, the value has to be halved. So again, for my class, I wouldn't ask you to do any calculations, just to be able to be familiar with the law of multiple proportions, law of conservation of mass as well. So just a summary, law of conservation of mass, the mass before and after a chemical reaction is the same. Law of constant composition, the type of atoms within a particular molecule are the same. Law of multiple proportions, when you combine elements A and B, their masses are always in small whole number ratios. As I said before with the example with nitrogen and oxygen. So we'll go from atoms to elements, and we'll talk about molecules and ionic compounds as well. So J.J. Thomson, again, came up with this idea. He discovered electrons through his experiments of cathode ray tubes. This is very similar to perhaps in your household before, back in the day. You would have these big TVs. Inside those TVs, not flat screen, but inside those TVs you'd have these cathode ray tubes, which actually show how we get different, your picture on your screen. So in this case we have a cathode, we have an anode, and we have electrons coming through this tube. And maybe some of you are aware, electrons are negatively charged. Therefore, the electrons will repel each other. So here, the electrons will repel each other, and they will move upward to the screen towards the positive end. So this was quite a big, nice discovery in a vacuum tube, how the electrons are negatively charged, going away from the negative end and going towards the positive end. He also postulated the plum pudding model, which is not correct. You can think of it as chocolate chips in a muffin. He thought that you'd have a bunch of, you can say, chocolate chips as our electrons in a big positive charge or a big positive sphere in our atom. And that's not true, as we know now that we know that electrons travel around the nucleus, which is composed of protons, which is positively charged, and neutrons, which are neutral. This is Rutherford's scattering experiment. I believe Rutherford was worked with Thomson. And in this case, we have alpha particles, which are positive charges. They go to the gold beam, or this is a thin gold foil here. A thin gold foil, and they thought that the positive beam of positive charges would go straight through. However, they discovered experimentally that some of the beams got deflected, some of them reflected back to the source, some of them went left and right, as you see here in this experiment. And they attributed this, if you look at the picture on the right, you see here that the positive charges, these purple balls, some of them went through, some of them got deflected when it hit the nucleus. Okay, so there was lots of empty space as well, but there was parts of the purple ball that got reflected and actually went through and got deflected as well. So here they came up with the idea that electrons are small and light and contained in a large space, and the nucleus, which is very small, but also it contains 99% of the mass of the atom, which we'll talk about later, is located in the middle of the atom, protons. So maybe some of you have seen this before. The nucleus, which is composed of protons and neutrons, is located in the middle of the atom, and we have electrons that circle around this nucleus. In continuing with Rutherford's work, we have here discovered that the atom here, average size of 1 × 10⁻⁸ centimeters, and the nucleus is about 1 × 10⁻13 centimeters. So if you guys can do the math, you guys should be able to convert this to meters. It's just an exercise from chapter 1. Recall that 1 meter equals to 100 centimeters. Okay, so yes, in this case, our nucleus is very small compared to the electron region. And also note here that 1 angstrom is equal to 1 × 10⁻10 meters. So we have again the nucleus, which is composed of protons and neutrons. They have a charge of +1 and 0 respectively. And we designate this as a mass of 1 and 1 AMU, which we'll talk about in a second. The electron has a charge of -1, so it's negatively charged, and we give it a mass of 0. The difference between the mass of proton and an electron is approximately 2,000 times lighter. So the electron is approximately 2,000 times lighter than the proton. In terms of mass, it's very minute. It has a small, it contributes very, very, very small to the overall mass of the atom. Therefore, we neglect it and give it a mass of 0. So 1 AMU here, atomic mass unit, is equal to 1.6605 times 10⁻27 kilograms. Of course, that's a very small mass compared to what we work with in our daily lives. And the electron is even smaller at 9.1 times 10⁻31 kilograms. So we use the atomic mass unit instead, because if we're talking in general, it's easier to say 1 atomic mass unit as opposed to the mass of hydrogen, which is 1 proton and 1 electron. Instead of saying the mass of the proton is 1.6605 times 10⁻27 kilograms, we can say it's 1 proton, 1 AMU, relatively speaking, average. So as I said here, if you look at point number 1, the mass of the proton is about 1900 times greater than that of an electron, and therefore we can neglect the mass of the electron, hence we give it a value of 0. And overall, the charge on atoms is 0. Usually you have the same number of protons and electrons for a given element. So we have 2 new terms here. We have the atomic number, which is the total number of protons in an atom, and we have the mass number, which is the total number of protons plus neutrons. Again, protons and neutrons are located in the middle of the atom. So if we just look at the first atom in general, hydrogen atom, it has an atomic mass of 1 and a mass number of 1. And we deduce this because there are 0 neutrons in the most simple hydrogen atom case. We'll talk about isotopes later, but in this case we have a mass number of 1 in green, atomic number 1 in purple. And H stands for symbol of an element. The mass number, except for the case of hydrogen, will always be greater than the atomic number. I'll repeat what I just said. The mass number will always be greater than the atomic number. In this case, this is the exception. Hydrogen, they'll have the same amount of protons, and well, there's 0 neutrons, so the mass number will also be 1, because as I said earlier, The mass number is defined as the number of protons plus neutrons. So here we have a hydrogen atom. Atomic number is 1. The mass number is 1. Hydrogen typically has 1 proton and has 1 electron, which goes around the nucleus. If we look at another example here, the carbon atom is made up of 6 protons, 6 neutrons, and 6 electrons. So we can calculate a mass number of 12, because 6 plus 6 protons plus 6 neutrons gives us a mass number of 12. And here, again, our mass number is in green, 12 for carbon, and for the atomic number is 6, so that means there are 6 protons in the nucleus. If I were to change the number of protons from 6 to 7 or 6 to 5, it would no longer be carbon. The protons, or the atomic number, is what defines the particular element. So again, this is our carbon atom, which contains 6 protons, 6 electrons. If we know the mass number is 12, we can do the math and figure out that the number of neutrons is 6. 12 minus 6 will give us 6, which tells us the number of neutrons. So as I said in the previous slide, the element, or the identity of the element, is determined by its atomic number. So in the case of hydrogen, we have something called isotopes, which I'll show you in the next slide, I believe. And the isotope is defined as the same number of protons but different number of neutrons. So in this case, we have another form of hydrogen, we call it deuterium. It has a mass number of 2 because it also has 1 neutron in it. Here at the top, isotope, atoms with identical atomic number, identical protons, but different mass number. So the regular hydrogen, 1 proton, 0 neutrons, a deuterium, 1 proton, 1 neutron, and a tritium, 1 proton and 2 neutrons. And this difference in mass number will also contributes to why on the periodic table the average mass of hydrogen is 1.007, okay, not just 1, and we'll show you that in a later slide. For carbon, we call this carbon 12, which is the most common one, 6 protons and 6 neutrons. We also have carbon 13 and carbon 14. Carbon 14 has 6 protons and 8 neutrons. All of us have these 3 different forms of carbon in our body, because we're made up of carbon, whether it's in a tree or in paper, which is made up of carbon. It is composed of mostly carbon 12, a little bit of carbon 13, and a very small amount of carbon 14. As I said earlier, the average mass for hydrogen is 1.0079. That's attributed to hydrogen having isotopes, and that of carbon 12.01. That's again attributed to carbon 12, mostly being carbon 12, but also you have a little bit of carbon 13 and carbon 14, and we'll do the math in a second to show the reason why it's not just 12. So just a small exercise. How many protons, neutrons, and electrons are found in each of the following isotopes? In this case, we have a mass number of 64. Cu is copper. And we have 29 protons. If we do the math, 64 minus 29. Let's do this on so that I don't get confused. 64 minus 29. 5, 35 neutrons, okay? Again, to find the number of neutrons, it's mass number minus atomic number. In the following case, which isotope corresponds to an element with 24 protons and 28 neutrons? So again, we have here, as I said, the smaller number within a particular element will be the atomic number. So right away, you look for 24 protons. And the mass number is 52, so 24 plus 28 in the question should give us 52. So which isotope? Chromium, Cr, corresponds to the data that was provided. So as I said before, we have here, we're going to focus on carbon 12 and carbon 13. I wanted you to calculate or show you how we came about the number 12.01 AMU. Again, AMU stands for atomic mass unit, the unit we'll use now for elements. So carbon 12, which is mostly made up of 98%, 0.93 made up of carbon 12. There's also some carbon 13, 1.07%. There's also a little of carbon 14, but we won't put that in the calculation as well. So we focus on carbon 12 and carbon 13. We see here, we take carbon 12 multiplied by its percentage, and carbon 13 multiplied by its percentage. We must convert those percentages to decimals, so we divide by 100. We divide by 100 here. We divide by 100, and when we do the math, we come out with 12.01 AMU. This is the general formula to find the atomic weight. It's the sum of the isotope masses times its percentage of natural abundance divided by 100. So in this case, if you remember for hydrogen, the mass of hydrogen on the periodic table is not 1, is 1.0079, and that's attributed to hydrogen having different isotopes. Here we have 99.985% for hydrogen in green, and for deuterium 0.015% for deuterium. When you do the math again, you take the percentages, convert it to decimals, take the percentage, convert it to decimal, and you do the math, you'll get 1.0079 AMU. The following is a question I want you guys to try. So chlorine exists as 2 isotopes. If you remember, I'm going to put the answer, the step-by-step answers on Blackboard, but I want you guys to try on your own first. If you don't know, put a question mark, at least write a formula. The question here states the chlorine exists as 2 isotopes, chlorine 37 and chlorine 35. They give you their respective percentages, 24.47% and 75.35% respectively. And they also give you the final answer, the average atomic mass of 35.46 AMU. So you need to find the atomic mass of carbon or of chlorine 35. So I'll give you a minute, or you can pause the video. I would set it up for you. In this case, you have 36.96590 multiplied by its percentage, 24.47. However, we said you have to reduce it to a decimal, so you divide by 100 to give us 0.2447. And then you add the second isotope here. We have carbon 35, which we don't know its mass. That's what we're trying to figure out, times 75.53%. We must convert it to a decimal, so we divide by 100 to give us 0.7553. And all this equals to 35.46 AMU. And I will let you use your math skills to figure out what the value of X is. So we continue on with the periodic table. We'll focus on some of the trends in the periodic table, some naming as well. When you encounter chemical symbols, it's very important to distinguish. If you have the identical letters, it's very important when you write it out, what you're trying to tell your reader, you should have the proper capitalization of the letters. So in this case, some people would get confused. HF, both of them should be capitalized to give you hydrogen fluoride versus the element hafnium, which is H little f. This is the same case for carbon monoxide. That should be 2 capitals versus big C, little c, that's cobalt. Okay, so it's very important to capitalize and be aware of what you're capitalizing in your elements. This is a periodic table, which we'll talk about in great detail. As I said, the number here, 7 for nitrogen, N is the symbol for nitrogen. It has an atomic number of 7, meaning it has 7 protons. If we had 8 protons, it would no longer be called nitrogen. It would be oxygen. The next one is gold here, again 79 protons. The atomic number is 79. And this was a periodic table. There are trends in the periodic table. This is discovered in the 1800s by Dmitry Ivanovich Mendeleev. So we have these rows which go from left to right. We have columns going up and down. We'll use the term period for rows and groups for column. And in general, going down a particular group, they in general, not all the time, but most of the time, they share the same chemical properties. We have here group 1, group 2A, these are our main group elements, group 3A, 4A, 5A, 6A, 7A, 8A, and in the middle we have transition metals of the periodic table. So here alkaline metals are group 1A, alkaline earth metals are group 2A, halogens group 7A, group 8A noble gases, group 6A is chalcogens, you don't need to know this, and again the middle one is transition metals. You do need to know group 1A is alkali metal, group 2A is alkaline earth metals, halogens group 7A, noble gases group 8A. Non-metals are located on the left side of the periodic table. Metals are located on the left side of the periodic table, non-metals on the right side of the periodic table, and we have this gray area, metalloids, which has characteristics of both located in the middle. There's this staircase here that really defines to the left are non-metals, to the right are non-metals, to the left are metals. Some characteristics of metals. They are solid at room temperature in general. They conduct electricity well. They have high melting points and densities. They are malleable. They can be bent, you can say with a hammer. Some characteristics of non-metals. They have low melting points, low density. They're not conductors of electricity and heat. They're not very shiny. And they do like to react with non-metals. They like to react with metals, non-metals and metals. some characteristics of metalloids. They possess both properties of metals and non-metals as well. So typically on an exam, you'll get a periodic table, of course. So you should be familiar with the, I would say the first 35, 36 elements. When I say first 35, 36, that's the atomic number 1 to 35, 36. Just be in generals. That'll help you speed up when you have to name compounds. So I'll help you out here. I'll give you the symbols, Mg. So the question is, are these metals, non-metals, metalloids, or are they located on the left of the periodic table or the right, or in the gray area? Oxygen is O, arsenic is As, and copper is Cu. So I'll let you guys figure out where on the periodic table that is. You can tell us if it's a metal, non-metal, or metalloid. If you recall, the atomic number here, and we have an atomic weight, and here the atomic symbol. We're looking at hydrogen as the element name. It has atomic number of 1 and an atomic weight of 1.0079. We defined, or we explained why it's not just 1, but 1.0079 because of the isotopes. So we have molecules and molecular compounds. A molecule is an assembly of 2 or more chemically bound atoms that can behave as a single distinct object. And versus a compound, the names are just slightly a little bit different in terms of their definition. For instance, it says a compound is at least 2 different elements. So for instance, if I ask you about the oxygen that you breathe in and out, O2, that is a molecule, but it is not a compound because O2 is 2 oxygen molecules coming together. So they are the same element. So an oxygen molecule, O2 is a molecule. NaCl, sodium chloride, is a compound. Can also be defined. So those are the 2 distinct differences. General molecules, they can be more different, but they have to be the same. The compounds cannot be the same. The compounds have to be different elements. They come together. As I just said, these are examples of molecules and not compounds because they have the same. They are the same. So all compounds are molecules, but not all molecules are compounds. Here we have the molecular formula, which shows the actual number and type of atoms. And we have the empirical formula. This is a new term, which shows us the smallest whole number ratio of the particular 2 elements coming together. So in this case, we have the molecular formula of H2O2, hydrogen peroxide. Its empirical formula, if we bring it down to its most basic, so we divided both the H2 and the O2 divided by 2, would give us HO for the empirical formula. Here are different ways to connect or draw these particular elements. We have here the molecular formula and the structural formula. We have different ways to express it in terms of 3D. You'll learn this more in organic chemistry as well. We have here the structural formula, the perspective drawing. We have the hydrogen going in and out of the board. We have here the ball and stick and the space filling model as well. So we'll take a break here and we'll come back with part 2 later on.